Okay. If you want, you can check the announcement I sent you over the weekend about the classwork. So I basically gave you like a kind of three scores, one for my lab, the other for the recitations, and the other for like the remaining stuff, which was like about the optional, well, not optional, but the quick videos on Canvas and the Grayscope, which I kind of just like merged into a single rubric. So if you have like, on each assignment announcement, I kind of tell you what's the maximum number of points you could get. And if you have them all, then you're good to go. If not, you can email me and I'll tell you what you would need to do to get the remaining points. Um, for today, oh, and I also sent you an announcement about like some videos which are useful to watch. Um, about the like divergence flux and all that stuff in case you want to have some like better intuition of what's going on, like physically speaking. The idea for today is to start like one of the big three theorems of the course. So basically like I like to draw it as a triforce. So like in like one of the three main theorems of calculus is called Green's theorem, uh, which I'll tell you about today. This is all for like your Green's theorems is for curves on the plane. So this is going to be on the xy plane. Okay. So this is entirely two-dimensional. So then if you want like a version of Green's theorem that works in space, like in 3D, then there's two possible ways to do it. Basically, because this actually will come in two different like pieces. So like there are like two versions of Green's theorem. So one version in 3 dimensions becomes what's known as Stokes' theorem. This is actually related to work, which is what we have been discussing so far. And the other version of Green's theorem becomes Gauss' theorem or the divergence theorem. So like let me call it divergence because usually that's how divergence theorem. And that is for something called flux, which I'll tell you about today as well. At least like the beginnings of what flux is. We'll have to talk more about that next time on Wednesday. But so basically, yeah, if you want, you know, like to generalize Green's theorem, there are two ways to do it, and that's what you end up with the Stokes theorem and the divergence theorem. In terms of like what we actually need to learn to compute these things, like the only thing left is kind of like doing integrals over surfaces, which once we have discussed on Wednesday how to parameterize a surface, you'll see more or less like straightforward after you have the parameterization. So the important thing there will be how to parameterize surfaces, which I'll tell you about on Wednesday. But once you know how to parameterize surfaces, then like the theorems are just like formulas, and there's no really like skill that you have to learn for like the theorems. It's just like the formula, like the really important thing is to parameterize the surface. Which is actually easier than parameterizing a curve in a sense. So it's not as bad. It's just that you will end up with a double integral instead of like an ordinary integral. Okay, so let me tell you first about Green's theorem for work. Okay, so let's start talking about Green's theorem. So let's call it part one because there are like two parts to it. So part one, and this is for work. Okay. So the idea is that now you will apply this just to curves on the xy plane. So here you'll have a curve on the xy plane, which is closed. So let me just draw about like a couple of those. Like there's like so So one curve that's closed on the plane would be like some sort of like circle. Here's another one that you could take. A closed curve could be something like a triangle. So it can have like corners, like the curve is allowed to have corners, like a triangle. So I mean, in a sense, like you could think of the triangle as three segments, but they're kind of like joints. So I'm thinking like in that sense, I'm thinking about it as being like a single closed curve. Uh, or like something a little bit more like harder to describe, but you know, uh, that could also be a closed curve. So I'm thinking here like of a closed curve as some like a path where you just return to where you started. Okay, so like for example in the triangle, you could think, oh, maybe I start walking on this vertex, get to the next back vertex, then to the origin, and then back to where I started. So it would be like for us like a closed curve would be just like any curve where the initial and final points coincide. So okay. Um, usually when we have been discussing work, work has been done for integrals that go from the initial point to the final point, right? In this case, like both the initial and the final point will coincide because of the closed curve. So to specify the curve, usually what you do is instead like just saying whether you're going to walk along the curve in a sense like counterclockwise or clockwise. So the usual convention, like for historic reasons and for like the formula to come out the way that I'm going to write it, is for you to walk along the curve in a counterclockwise way. So just to show you what I mean, I'll put some arrows here. Okay, and so the read like again like the way one way to think about it is that if you thought about the curve as some sort of like border for a country, then the country being what's enclosed by the curve, then the country kind of lies to your left as you walk along the curve, if you think about it. So that's kind of like the convention that we're going to apply for it. Okay, so the that's also called like the orientation of the curve. So is that you travel counterclockwise. So move along the curve in a counterclockwise way. And then again, so far we have been finding work for a vector or like a force, a vector field. So let's say because we're working on the XY plane, it kind of like makes sense to just think that the vector has two components in the I and J direction. So let's say that you have like a vector or force F. Okay, so again, like the vector or force will have in this setup two components. So one component in the I direction, another component in the J direction, which I'm calling F1 and F2. If you read the book, then like, and this is kind of like a historical accident, like the components are usually called M and N, which is a little bit like I don't necessarily find that like the best notation for this context. So, but I'll still write it that way as well. So that is the other way that it's written. So for example, if the vector is like, I don't know, x squared plus y I plus 3 minus xy right? So the first entry is what I'm calling F1, but also like people refer to as M. So what would be F1 or also M. And this is what you would refer to as F2 or M. Okay, so both like what ways of writing it is like those are like the two natural ways. Well, I mean, I think F1, F2 is more natural, but yeah, it's not unusual to refer to the components as M and N. So if you do that, what do we know so far? If the force happens to be conservative, right, we already know the answer for the work, right, along a closed curve. I don't know if you remember, like when the force is conservative, like the work along a closed curve is zero, right? One way to not to figure that out is like, now that we know that a conservative force has a potential, the work equals the potential of the final point minus the initial point. But if the curve is closed, the points are the same. So like that would just give you zero. So when F is conservative, right? The work along a closed curve will be zero. Will be zero. And so what you can think of Green's theorem. So what Green's theorem does is kind of give you like a formula for what the work will be in more generality. So Green's theorem is so here's like the question: what if F is not conservative? Okay, and Green's theorem gives you like an alternative way of finding this work. So what Green's theorem does is computing the work. So let me write what it says. So here's Green's theorem. You have a closed curve. Let me draw like again like a closed curve. So these here a closed curve. And again, you're moving counterclockwise along this curve. Why do I want a closed curve? Because if the curve is closed, then it does like it's almost like redundant. It encloses a region, right? Like there's a region of the on the plane that's enclosed by the curve. So let me color it. So R is the region enclosed by the curve. So what Green's theorem says is that the work done by the force, so done by F, there's always a way to find this work directly. You just do like the integrals of the dot product between the force and the velocity vector of the curve. So it is possible to compute this like directly. What Green's theorem does is give you like an alternative way of finding this So what Green's theorem says is that this work equals equals a double integral that takes place on the region enclosed by the curve. And what do you integrate? You integrate like an odd combination of like the of like these partial derivatives, but essentially what you're integrating here, this thing like will this is actually the third component of the curl of the vector. So I'll put here this is like but again, the important thing of Green's theorem is that you can like instead of like computing the work directly, you can do like a double integral that will give you the same answer as the work computation. Um, Let me put it like in a box. I'll rewrite it somewhere else because I'll like actually let me use it. Let me put it here under the try first. So again, I'll show you with an example how this is supposed to work. But the idea is like instead of like computing the work directly, you can do like a double integral that will give you the same result. Why does that work? I can say I had done like a video about it, like a mini short, like a short video, like 10-minute video that explained it. But the idea, like without getting into too many details, because like it is somewhat a tedious proof. The idea is like if you have like a region, you kind of break it in, chop it, like you can break it into bunch of mini rectangles. And then you just verify the Green's theorem on a mini rectangle. On a mini rectangle, then you can use like a Taylor approximation to approximate everything. And then you kind of verify it by brute force. Like, it's not very, I mean, it is illuminating, but like it's a bit of a detour to even like the amount of time we have left. So, but I do kind of go through it in one of those like short videos if you want to kind of see where it comes from. But like long story short, like you check in on rectangles and then everything else is like by approximating like a region by rectangles, basically. Um, but it's kind of more useful just to see in practice how it works out so that you have like a better idea of what this is. Is that making sense? Okay, so let me show you how this works in practice. To show you like the actual advantages of like having Green's theorem at hand. So let's get this here and I'll do the calculation for you. And then I'll tell you about the flux, which is the second part for today's class. So Okay, let's do something very simple. Okay, so that's going to be the vector field, that's or the force. So okay. So let's say you wanted to find the work done by this force along a particular curve. So the curve that I'm going to take is going to be let's just take the triangle. Okay, so the curve is just like the you know the segment like the segments of the triangle or the sides of the triangle. So curve C is that the three sides of the triangle with vertices 0, 0, 1, 0, 1, comma 1. So the triangle has three sides. So like the curve is really like three mini curves like concatenated, right? Like one for each side. So let me call those like C1, C2, C3. So the work done by F, right? So like if you didn't have Green's theorem, like that's what I'm trying to do first. If I didn't know Green's theorem, what would I have to do in this problem? To find the total work. I would need to find the work along the first curve, or the first segment, I should say. The work done along the first segment, plus the work done along the second segment, plus the work done along the third segment. Is that making sense? So I would need to do three separate work computations. So let's do them, like they're not too long, but so let's work them out just to show you what happens. Okay. What is work? Okay, so work in general, this is like the definition of work that we have been working with. So the work is the dot product between the force and the velocity of the curve, right? So let's start with curve one, like, or the first segment of the triangle. And let's call this a vertices PQ and R. PQ and R, okay? So let's talk about let's do segment one from P to Q. Okay, so For any work computation, you need a parametrization of the curve, right? This is a line segment, so the parametrization of the curve is just, I'll put a 1 for like the third segment. It's the initial point plus p times the vector, right? Like the vector, you can take it from the vector being from p to q. Is that making sense? The initial point is 0, 0. And the vector PQ is Q minus P, right? Well, let me put it in like Q is 1, 0, and P 0, 0. So this just gives you the vector T comma 0. That's a parameterization of that line segment. Is that making sense? Okay, so that is the first parameterization. The corresponding velocity vector is easy, just like the derivative of that. So it's 1, 0, which makes sense because the first segment is completely horizontal. So a direction for this vector, like for this segment, should be like the vector I, right? It's just like pointing in that direction. Okay, and then the force F is y comma 2x in general, but you have to replace it in terms of the parameterization, right? So what is y in this case is 0 because you are like along this horizontal segment, which is at y equals 0. And what is 2x? X is t, so it's just 0 comma 2t, right? So what is the work along the first curve? Is the dot product from 0 to 1 of f dot v1. Again, so this is the dot product from 0 to t with 1 comma 0 dt. Okay, this dot product is 0, so like you're just integrating 0 dt. So there's no work done along the first curve. Does that make sense? Questions? Okay, so let's do that. And now we have to do that for segments 2 and 3. So I'll just go a little bit faster on those two because they're exactly the same idea. So let's do segment C2. So the second position vector, now you're going from Q to R. So it should be Q plus T times a vector, but the vector is now QR. So there's a vector QR here. So Q is 1, 0. And the vector QR is completely vertical, right? What you get by subtracting these two. So you just get 0, 1, which is the vector J. So just 1 comma T. Okay, that's the second parametrization of the curve. Okay. You find the corresponding velocity vector. The second velocity vector is the derivative of this, which just gives you 0, 1, which makes sense because the second curve is just completely vertical. So the direction should be vertical as well. And what is the force along the second segment is y comma 2x. What is y? Y is t. And what is 2x? Well, x is 1, so you just get t comma 2. So the work for the second segment is that dot product. Well, this goes from 0 to 1 because like at time 0 you are at q, at time 1 you are at r. So it just gives you t comma 2, that's the force, dot the velocity vector 0, 1 dt. So this dot product just gives you 2. Sorry, that's just 2. So the second work is just 2. Let me do segment 3 here. So for the third segment. What is the parameterization of that curve? It is initial point plus c times a vector. The vector is RP. So you get 1, 1 plus c times p minus r. So you get -1, -1. So it's 1 minus t, 1 minus t. Okay. What is the velocity vector? Is the derivative of that, so it's -1, -1. And what is the force along the third segment? The force, which is y, 2x. Y is 1 minus t. And x is also 1 minus t. So when you multiply by 2, you get 2 minus 2t. Okay. So the third work is the integral of the dot product between this force and this velocity vector. Okay, so this is t minus 1 plus 2t minus 2. So this is what? This gives you 3t. So you get 3t squared over 2 and minus 3t 0, 1. Okay, and that gives you 3 halves minus 3. So it's 3 halves. Okay, and so the total work would be the work along C1 plus work along C2 plus work along C3, which is 0 plus 2 minus 3 halves, and that gives you 1 half. That is what you would have to do if you wanted to find the work using like the standard formula for work that I had given you before. Does that make sense? Yeah.
Could you explain the notes for the for segment 3, 0, and 1?
Oh, for the time, you mean
Yeah, well, why you equate circle?
right. So the thing is like you have to think which values of t you have to plug in to get at the initial and final points, right? So if you plug in t equals 0, right? If you put t equals 0, you start at 1, 1. And if you put actually like hint, if you do a line segment in this way, it always goes from 0 to 1 in every single case. If you always do it from like if you take the vector to be p, like the vector goes from the initial to the final point, because you see like then when you put t equals 1, you get 0, 0. But like that actually works regardless. It's kind of like universal in that sense. If you use like the vector to be like PQ, like but yeah, good. So my point is that if you wanted to work for this curve, it's like a tedious it's not, each piece is relatively simple, but it's like a tedious computation, right? Because you have to do this 3 times basically. And Green's theorem is like kind of like a hammer that tells you no, like just do like a single double integral. Okay. So what is Green's theorem in this case? Maybe before just showing you that, like, is that any other things? Because at least I do have to erase this part. So what would Green's theorem say? It says that instead of having to do all those 3 single works and adding them, the net work is just a single double integral. So if what Green's theorem says is that the work is just a double integral of what? Of the derivative with respect to x of the second component of the force minus the derivative with respect to y of the first component of the force. So let's just work it out in this particular case, and then I'll put the bounds because it's supposed to be a double integral. What is the second component of the force in this case? That's 2x here, right? So the derivative with respect to x, 2x minus the derivative with respect to y of the first component, which is y. Okay. And so, well, this is 2 minus 1. Okay, so you do 2 minus 1. So this is what you're going to integrate, and it's a double integral. You know how to give bounds to a double integral. You can say that x goes from 0 to 1, for example, and y goes from 0 to x, right? And this is easy to do, right? Like, and then just like, okay, this is just 1. So you just get like the integral from 0 to 1 of x dx, which is just 1/2, right? Which is exactly this. So you can just go, I mean, you can compare just like the amount of time it takes to do like a single double integral versus time to do 3 separate integrals, which each requires their own parameterization, right? Like it is like dot products, taking velocities, blah, 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 a bunch of things. The only thing you have to notice is like in Green's theorem, this does refer to kind of like the network, if you want to call it that, meaning like it is like the total work of the 3 pieces. You cannot like isolate the work of a single piece from Green's theorem, right? If you wanted like the work done just by one of the segments, then you have to compute it separately. You know, what Green's theorem is tells you like in the net effect, like, you know, the total work is this double integral. It does carry less information from than having done like the 3 pieces under separately, but it's still like, you know, if the only thing that you care about is like the network, then that is more than enough. Okay. Is that making sense? Um, so that's how this part of the course kind of ties nicely to the stuff that we were doing about before about double integrals, for example, because now double integrals can appear as a way to find work. The version, like there is a version of that when the curve is in space, and for then like you need like Stokes theorem, which is like what Stokes theorem says is like if you have like a curve in space, which you can think kind of like as the edges of this net, then you do like an integral that takes place over the surface. And what you integrate is like the curl. I mean, the normal component of the curl. I'll tell you about that. At least I'll tell you about that Monday for sure. So, but so like there's like a, which is why I drew when I drew the triangle thing. There's a way to do kind of Green's theorem for curves in space, but for that, like the grown-up version is called Stokes theorem. And that's where we have to talk about surface integrals on Wednesday. And I'll tell you how that works. Okay, so hopefully this just shows you the advantage of having green theorems around. So every time you have a closed curve, I mean, for this type of problems, usually you will be told use green theorem to find the work or something to that effect. So it's not that there's like too much of like this decision process on your part, because you will be told to use green theorem, right? If the idea is for you to use green theorem. So, but I'm just saying like theoretically, like the thing to appreciate is that it can simplify a lot your computations, because you're going from having to do 3 integrals to just having to do like a single double integral. For example, if the curve had more pieces like an hexagon, right? Like then there would be, instead of doing 6 integrals, you're just doing 1. Like, so like there can be a lot of like trade-off, like, you know, in that sense. Okay, now the other thing that I have to tell you today, which is there's kind of less stuff to discuss for this topic, is called flux. At least when it comes to curves. So let me tell you about flux now. Okay, so what's the idea here? Um, let me see if I can explain it first with a picture. So imagine that you have some sort of like curve um, on the plane. So, for example, maybe there's like a river here on the plane. And then this kind of represents the coastline or whatever, right? So you have a bunch of people swimming, or you have some fish swimming on the river, and then you want, well, I mean, I guess like, yeah, maybe you don't want the fish to walk into the sand, but like, like you can just ask like, okay, like imagine that you have like a bunch of like stuff moving on the river, like so you have some substance moving on the river, so it could be boats, it could be people, fish, whatever. And you want to know how many go through like pass through the curve in a given amount of time. So if you thought about this more like in terms of like transportation, like it could be like bunch of ships carrying like with containers, and they're just crossing like a some sort of like border or whatever between countries or like on the ocean. So you have some, let me draw some shapes here. Well, so yeah, like they're kind of moving, doing whatever they want, but eventually they want to cross to the other side, right? So in order to cross, they have to pass through this curve. So you get here, okay? And so you want to know how flux is kind of related to how much stuff is passing through a curve um, in a given amount of time. So there are two notions of flux. Um, like let's call this flux through a curve because it can be confusing, or like flux for curves. The other notion of flux would be for surfaces, which is like, oh, you have now you have something in space, and then you want to see like how much stuff is passing through like a given surface, like like a net that you put in space. Okay, so that would be for surfaces, but it's kind of like the same idea. So flux is related to how much material or amount of stuff is going through like passing through like a curve in this case. So and how are we going to think about the stuff? So just imagine that there's like a vector that tells you how this stuff is moving. So in the case of boats, there will be like a vector that's telling you the velocity of the boats. Or if you're thinking about just like fish swimming on the river, like it's just like the velocity of the river of the fish. So what we're going to have is some sort of vector, which I'm going to keep calling f. So I have some vector f, which tells you how this stuff is moving on the plane, okay? So it's, you can think about it like some sort of like velocity vector of the material. I don't want to call it V because V is kind of reserved for the velocity of the curve. That's why I'm keep referring to it as F. Okay, so let's just like zoom in like in this situation, like like let me show you a bit better like what's going on. So like imagine like you have like the ships that they're kind of trying to cross through this curve, like through this border, right? Or like the cars or whatever. You want to think about it. And so you get to this point. In order to cross, like in order to cross to the other side, you do have to pass through the curve. There's no jumping allowed. So that's why we're thinking about the situation being on the plane. So once you get here, once you get to the edge, like to the border, to this curve, you have like a vector that tells you the velocity that this ship was carrying, or like the velocity of the ship at that point. Okay. Now the idea is that in order to pass, like this, like the part that's a little bit hard to explain. In order to pass through the curve, right? If you think about this as a velocity vector, you don't need to know all the information about this velocity vector. What really matters is like the component of the vector that's perpendicular to the curve, if that makes sense. So this vector kind of can be broken into two pieces. One that is perpendicular to the curve and the other that's kind of tangent to the curve, right? And of those, like, if like of these two pieces, like the one that's responsible for you moving through the curve is the perpendicular one, because the tangent one is just literally moving you along the curve, if that makes sense. So the component that's perpendicular to the curve um, is kind of like is the one responsible for like, you know, is the one responsible for crossing the curve, or something crossing the curve. Is that making sense? So once you reach to the edge of the curve, if your velocity vector, like, if you think of the edge of the curve kind of being like as a wall, the part that's like responsible, for you crossing the wall is like the component that's literally perpendicular to it. The other one that's tangential is like literally just moves you along the wall. So the idea is that the normal component of the force is the one that kind of measures how much stuff is passing through. And so kind of the flux is just like a sum of all those contributions. And the way to do the sum here is to do like an integral. So just to write down the formula. The flux is going to be, so the flux of F through the curve C, is going to be an integral between F and N where here N is a normal vector to the curve. So let me draw it for you in this picture. So here N is a vector perpendicular to the curve. And like here it's like from time one to time two. Like, initial time. So the only difference between flux and work in terms of a formula is that work uses the dot product with the velocity vector of the curve, and the flux uses the dot product with the normal vector of the curve. That is the like, so let me write it as a remark. Notice that work is the dot product between F and the velocity vector of the curve. So they're basically identical formulas, except for, again, the fact that one one uses the velocity vector and the other the normal vector. Yes, sir.
But here n is the unit.
Oh, so just as a notation, like, so the way I'm going to take it, like, if I wanted to take it with respect to the unit normal vector, I would put the S here for like the arc length. The way I'm doing it, I'm kind of like assuming already like a parametrization. So n will be normal vector, but with the same magnitude as the velocity vector. So it's not going in like the way I'm writing the formula, it won't be the unit normal vector, but you can write it in those terms. But I'm going to actually, that was my next step, like how to take n. So what is n here? Well, how can you produce a vector that's perpendicular to the curve? Let's just think about it quickly, like, you know. If you remember, the only real way we have had here in this course to create normal perpendicular vectors is using some sort of like cross product, right? That's the easiest way for us to create a perpendicular vector. So one way to make something perpendicular to the curve is to take the cross product between the velocity vector and the vector k, because k 0, 0, 1 is always perpendicular to the curve, given that the curve is always on the plane. So the way we're going to think about this vector, normal vector, is as v cross k. Okay, where here v, let me write it in a second. So v is going to be dx dt dy dt comma 0, because like the curve is on the plane, so there's no third component for the velocity vector, and k is 0, 0, 1. So if you do that, it's kind of like easy to check that the cross product in this case is just minus, sorry, it's dy dt dx dt comma 0. And that, oh, sorry, there's a minus here. And that will be our choice of normal vector. So the way I'm writing it, it does have the same magnitude as the velocity vector. But there, yeah, there is a way to write it using the normal vector. Okay, so just, yeah.
Does it matter if you do v cross k versus like negative v cross k?
Oh, so the only reason why I'm right, yes, that's a very important question. So the only reason why I'm putting it this way, let me, yeah, is that when the curve is closed, this matches the vector that points away from the curve, and that's why sometimes it's called outward flux. So you could have done the other option, like it would only differ by a sign from this one, right? But the convention is just chosen so that this vector kind of points away from the curve. I'll actually show it for you in a second, like once I do this example. So let me just write everything down again, like more concretely. So what I'm trying to say is that the flux is going to be this, where the normal vector is dy dt, comma, minus the x dt, comma, 0. This formula is on the formula sheet on the final, by the way, but, for the normal vector, but, still useful too. Know how to do it on their own. Okay, so let me show you an example where I compute the flux, and I'll tell, like, after I've done that, I'll write for you grades here. So let's think about the curve. Okay, here's an example. So the curve is going to be the parabola. So parabola y equals x squared. So let's say this is y equals x squared from between the points -1, 1 to 1, 1, between -1, 1 to 1, 1, together with the segment from 1, 1 to -1, 1. Together. You want from 1, 1 to -1. So it's what you see there in that curve. And let's say that f, the vector f, just to make this easy, I'll do it, I'll say that f is xi plus yj.
Should we parameterize it counterclockwise?
So for us, whenever it's a closed curve, yes, the convention will always be counterclockwise. Correct, yeah. And you'll see that because of that convention, that's why I wanted to do this example first. Like the normal vector will be pointing away from the region enclosed by this curve. So the flux, it's kind of like really think about the computation as being similar to work. If you wanted to find like we're kind of trying to like just imagine like you have some material, some fluid moving through this region, and you want to see how much is passing through the edges or the borders. So the borders consist here of two pieces, right? Like one is the curve, the segment, and the other is part of the parabola. So the flux should be the flux through the segment plus the flux through the parabola, if that makes sense. In the same way, which work would have been the work through the segment plus the work through the parabola. So let's go this C1 and C2. So what I'm trying to say is that the flux is the flux through the line segment Okay. So what is the flux through the segment? Let's call this P and Q. So I need a let's start there. Like I need a parameterization of this flux. So it's exactly the same thing that we were doing for work before, but instead of taking the dot product with the velocity vector of the curve, we take the dot product with the normal vector of the curve. So let's parameterize first the curve. So let's call that C1, like, so it's like the parameterization of the curve. It's the point plus v times the vector. The point is 1, 1. And the vector, if you subtract these, like it gives you negative 2, 0. So that gives you 1 minus 2t, comma 1. Okay, that is a parameterization of this line segment. Okay. And you see, like t goes from 0 to 1, always goes from 0 to 1 if you do the parameterization this way. What's the corresponding velocity vector? The velocity vector is just minus 2, 0. Okay. Which makes sense because this curve you're moving in the negative x direction, so that's why the velocity vector is minus 2i if you think about it. And what is the normal vector? The normal vector, if you look at the formula, is dy dt. Actually, you can ignore the third entry. I mean, like the third entry is always 0 because these vectors are on the plane, so you don't need to put it. So it is dy dt, comma minus dx dt. Okay, so what is dy dt? That's the derivative of the second component with respect to t. So let me just write it explicitly. The second component is 1. And what is this one is 1 minus 2t. Okay, so what does that give you? Like the derivative of 1 is 0. So you get 0, comma. Sorry, this should have been a t. So minus 2 with a minus gives you 2. So it gives you 2j. So it's kind of nice to see like this explicitly. What I'm saying is that the normal vector into this curve at that point is like what I'm saying is that the normal vector to the curve is 2j here. Is that making sense? So you see, like it points away from the region enclosed by the curve, and that's why it's being like that's just why sometimes it's called like outward flux, because you're looking at like the normal vector that points away from the region. But since like this is the only one we'll compute, I'll just call it flux in general. Once you have that, you can parameterize the vector f. So what is the vector f along this curve? The vector was x comma y, but x is 1 minus 2t, and y is 1. So that is what the vector f is along this curve. Okay, and so the flux is the dot product from 0 to 1 of f with n. And the second normal vector is, sorry, the first normal vector is 0, 2. So you just get 2 dt. Okay. So the stuff that's going through the line segment is 2 in whatever units like you're using. It's like you usually flux is like kind of like mass per unit size. Like, it would have like if you wanted to think about it in terms of like a mass going through Sure, we would do maybe like kilograms per second or something like that. It's kind of like a rate. Um, so that is what the first flux gives you. So it's exactly what we were doing for work. The only difference is that now you have to find the normal vector and take the dot product of that. But everything else, more or less look the same. That making sense so far so good? And then you do the same for the parabola. So, what is the formula for what is the flux through the parabola? Let's put it here. I think I have enough room. So, what is flux through the parabola? So you parameterize the parabola. We had discussed it before, but how do you parameterize a parabola? If you take the point on the parabola, that's x comma x squared, right? And like, so everything is being given in terms of x, and the usual parameterization is just to rewrite x as t. Okay, so you get t comma t squared. So the parameterization for the parabola is t comma t squared. Okay, the velocity, the corresponding velocity vector is 1 comma 2t, and the corresponding normal vector to this is like the y dt comma minus the x dt. The second entry is t squared, so and the first entry is t, so that gives you 2t comma negative 1. Okay, so that is the second normal vector to that is the normal vector to this curve. So you see, like, this vector always has negative second component, so it's always pointing south in a sense. So it makes sense to be pointing away from. Kind of looks like this. And now what is the second? What is the force along the second curve? The force was x comma y, and that is x is now t, and y is t squared. So the flux in this case would be the now t, from which values does t go? From -1 to 1, right? So this one is not 0 to 1. So from -1 to 1 of f, which is t comma t squared, the normal vector is 2t comma -1. So this gives you 2t squared, right? Minus t squared dt. So this is like the integral from -1 to 1 of t squared dt. Well, that's going to be 0 because like it's symmetric, right? It's an even function. Or no, no, sorry, like this is t cubed over 3. Like it would have been like if it had been t cubed, yeah. So it's like 2/3, right? Good. But even better. So so that is the amount of stuff passing through the parabola part. So how much stuff is passing in general? Like it's 2 plus 2/3, right? Like that, like the net flux, the total flux is 2 plus 2/3, which is what? 8/3. Okay. So far so good. That making sense. And then you say, okay, so to find the net flux, to find the flux in a problem like this, you find the flux through the first piece plus the flux through the second piece. If they had been like a triangle, like in the first example, that we did with work, it would have been flux along the first segment plus flux along the second segment plus flux along the third segment. And then at that point, you say, well, wouldn't it be nice if there were like a formula that tells you that that is the same as a double integral? And yes, there is a Green's theorem that says that this actually coincides with the value of a double integral. So it's like an easy formula. So let me write it down. We have time to write it down. So there's like a version of Green that's called Green's theorem for flux. For flux, Green's theorem for flux. Which says, and I'll explain what, like next time I'll tell you more. Once we get to the divergence theorem, I'll tell you more what's this stuff that appears inside the integral. For now, we'll just take it a bit of a black box, but it's called the divergence of the vector. But I'll explain that later. Like I just want to get to be at least be able to write the formula. So in Green's theorem for the flux, the idea is that if you have a closed curve and you have this normal vector that points away from the curve, and you have your vector f, which is f1 comma f2, or n comma n, which again is not like the best notation. What Green says is that the flux, and here's like the double integral. Now, according to Green's theorem, you can do the flux as a single double integral over the region enclosed by the curve, but what you integrate is something different, which again, I'll tell you what that is next time. Or, but that's called the divergence of the vector. But I'll just keep it as a black box for now. So what you integrate in this double integral is that combination of partial derivatives, which is called the divergence of the vector f. Okay. So in our example, sorry that I went a bit fast today, but like in our example, what does that mean? It means that the flux, if we believe this formula, should be the integral of the derivative, which is like in our example where f is x comma y, should be the derivative with respect to x of the first entry of the vector, plus the derivative with respect to y of the second entry of the vector. So this is 1 plus 1, which is 2. Okay. And what are the bounds? Like this is a double integral, which hopefully you remember how to do it. Like x goes from -1 to 1. And y goes from x squared to 1, right? So you end up having to do like the integral from -1 to 1 of what? 2, 1 minus x squared dx. Well, and hopefully that will be 8/3, right? If you do it like, check that gives you 8/3. It should give you 8/3 because we already found that, this doesn't work. So like, it should give you like the same result. So what I'm trying to say is that instead of like computing the flux directly, you can do like a double integral instead that gives you the same answer. But again, this kind of gives you like the combined flux. It cannot isolate the flux from the parabola or the flux from the line segment. So it just gives you like the total amount. Again, if you want to think about it in terms of substance, all the substance that was passing through this line and through the parabola. If you want to know just one of the components, you do have to find the flux directly separately as like the integrals that we were doing before. Okay, so. Yeah, let's start here, like what I'll tell you on Wednesday is like, what, how to do the flux for surfaces, which is like a bit more interesting and because it requires like parameterizing a surface and doing other. Yeah.
Didn't you ask us say bias?